Okay, can you guys find the notes we did yesterday? I skipped over a couple of slides. I figure maybe a good place to start today, just a bit of review of some of this concept we talked about yesterday, and then we'll keep moving on. And if we finish permutations and you guys feel like you want to try doing combinations just to get a day ahead, we can do that. If you want to just take one lesson at a time, that's fine too. I don't care. We'll play it by ear once we get a little further ahead. So, can you guys find this slide from yesterday though, or I don't know? Write it down. Sorry. Pull out your notes from yesterday. I just thought maybe we should do some examples of the things we talked about yesterday first before we move on. Find the slide, yesterday's notes. I skipped over a couple of slides. Why don't we start with just a review of a couple of those things? So, while you're doing that, maybe just listen while I kind of remind you what combinatorics is. Maybe I should start with what it isn't. There's no graphs, which is nice. There's no equations, which is nice, kind of. Combinatorics is a very different unit of math, a very different branch of mathematics. It's very, very similar to like logic, reasoning type math skills. I'll say this a lot over the next couple of weeks. The math is not hard. Like the math is usually multiplying or adding numbers. Well, everyone should be able to more or less handle that. I mean, don't make your mistake on that part. The harder part is interpreting the question. Almost everything is going to be some sort of word problem or puzzle. And it's your job to try to figure out how to solve that puzzle. Most of these things involve the arrangement of objects. Combinations and permutations and probability. I talked yesterday about like there's gambling overlap in this section. Statistics sometimes overlaps with this as well. Some people really like this section. Some people really hate this section. Usually I find kids they're one or the other. It's either like their favorite because they're like, ooh, this is kind of fun. Or they very much dislike it because they'd rather just have like an equation to solve. There's like there's no algebra skills even. So, some of the things we talked about last day then. The first main thing is called the fundamental counting principle. And after a while, I just started doing this every time I solved a problem. And we would just multiply different numbers together. Often it might be something like 2 times 2 times 2 times 2. And that would be, for whatever the question was, that's a way of solving it. Or perhaps after a while, some sorts of questions involved 4 times 3 times 2 times 1. And I showed you a little trick that mathematicians have come up with to kind of simplify any scenario where the numbers that you multiply by always descend by 1. This was known as 4 factorial, which is that exclamation mark. It's just a faster way of representing the fact that like you've got 4 people, and then one of them's gone. So then there's 3 people, and one of them's gone, and then there's 2 people. This actually reminds me of one of Kinsey Ann's Sesame Street songs. Where it's like there were 4 things, and then there's 3 things, and then there's 2 things, and then there's 1 thing. Why don't we multiply by the 0 things? Yeah, we can't multiply by 0, right? Because if you times by 0, then the whole thing kind of washes out, right? So we do stop whenever you get to 1, so never multiply by 0. Okay. There are some scenarios. Yesterday I talked about one with like a ski
Mr.
lodge.
Cleaver, can you please call 100? Mr. Cleaver, please call 100.
There was one yesterday with a ski lodge where there's like 11 people but only 9 jobs. And so 2 people don't get to go to work, if that makes sense. And so this would be something like, say, 5 times 4 times 3. The other 2 people, like the person who would be number 2 and the person who would be number 1, they apparently don't have a job for the day. So do you guys remember the way we can write this in factorial notation? You guys remember it all?
Factorial over 2 factorial.
Good, that's it.
Or just 2?
2 would work, but 2 factorial works probably just as well. The logic behind this is really 5 times 4 times 3 times 2 times 1. And then if we divide by 2 times 1, the 2 times 1s will cancel. And so this is a very common scenario where it has to go in descending order because as soon as someone's selected, they're out of the running, so you can't count them again. But not everything gets used. There were a couple of other twist type questions. One of them I like to call like the Brangelina question, where Brad and Angelina have now gotten married. They are so intertwined with each other that they're essentially one person. Do you guys remember the twist as to how to solve a question like that, where 2 people are really like 1 people? Remember how I showed you do that yesterday? Say there's supposed to be 6 people. Say that letter.
When it comes as 1, but it looks signed as 2 because they can like switch positions.
Okay, so like pretend these people right here have to be together. Rather than having 6 objects, you only have 5 objects. So this is 1, 2, 3, 4, 5 objects. Like Brianna said though, these people can switch. So the answer is 5 factorial times 2. Because you could go A then B and then everybody else, or you could go B and A and everyone else. It's like a double thing. The follow-up twist to that one is, what if Brad and Angelina break up? They're no longer Brangelina, and so they can't stand to be next to each other. Celebrity divorce, right? And but they have to be in the same picture, so we need them to be in the same row, but there has to be at least one person in between.
Subtract all the ones where they're together. So take the total numbers, subtract 5 factorial.
Good. Yeah, so the way you'd solve that is if Brad and Angelina can't be next to each other. That's why I also pick A and B, because A and B works well. Okay. You guys working on, or are you just getting caught up here?
Yeah.
Okay. If you have to have them not together, basically make there's 6 people total, and then subtract the ways in which they are together, and that will be the ways in which they are not together. So those are some of the first twists we've talked about. Today I'm just going to add more and more scenarios. But okay, why don't we try some of these questions here that I've got there. Let's just do these as a group. So this question here, how many ways can 7 books be arranged on the shelf if all of the books are different? So you can kind of envision you've got book A, book B, book C, D, E, F, and G. How many choices do you have for the first place on the bookshelf? 7. And then once that book is used, then you have 6 and then 5. And after a while, we don't even do that anymore. You just say the answer is 7 factorial. Does that make sense? But let's say that for some reason you own 2 copies of, I don't know, Oliver Twist. And like those 2 copies of Oliver Twist are like the exact same as each other, to the point where you can't even tell the difference if you open them up, because there are no distinguishable differences. Essentially, there's identical objects. So you don't really have A, B, C, D, E, F, G. You actually have A, B, C, D, E, F, F. And 2 of the letters are the same. I actually didn't talk about this twist when I kind of was reviewing stuff. Do you guys remember how to deal with identical looking objects? What do you do with that twist?
Divided by the number of similar objects.
Good, yeah. So there are 7 total objects, but because these 2 F's right here look the same as each other, you're going to divide by 2 factorial. Technically, you should also divide by 1 factorial for this one, 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 and 2 factorial for that one. But why bother dividing by all those 1 factorials, right? Like, you just divide by 1. Does that make sense? Okay. Next twist. What if the books are different again, but there must be a math book on an end? So I'm going to try to like visualize this. You've got your 1, 2, 3, 4, 5, 6, 7 right here. There must be a math book on one of the ends. You have 2 possibilities. What if the math book is on the first end? Well, if the math book has to be here, how many choices do you have for this slot right here? No, just 1. It has to be a math book right here. Does that make sense?
Well, it could be on either end though.
Okay, so then I'm going to do another possibility in a second here. 1, 2, 3, 4, 5, 6, 7. Or the math book could be on that end. Does that make sense? I'm kind of showing you 2 different possibilities. Could be the starting book, or it could be the ending book. Well, let's say the math book goes right here. How many choices do you have for the rest of the books then? Well, then you have 6 choices here, and 5, and 4, and 3, and 2, and 1. Or if the math book is on the other end, what you really have is 6, 5, 4, 3, 2, 1, and then the math book. So here the math book is first, or here the math book is last. Really, this row of numbers right here is 6 factorial. This row of numbers right here is 6 factorial. What does or mean? You add them, yeah. So your final answer is, you can either write it as 6 factorial, where the math book is first, plus 6 factorial, where the math book is last. There is another way of writing this, though. If you have 6 factorial and you add another 6 factorial, you have 2 6 factorials. that make sense? Okay, this next twist. 4 books must be together. What's that twist like? Yeah, it's like Brad and Jelena. Only, this is kind of weird, rather than 2 people being together in a couple, it's like a 4-person couple. So, okay, I guess the analogy kind of breaks down, but basically those 4 books are now one intertwined object. So if I kind of write them all out, I'm just going to write them out again, like say A, B, C, D, E, F, G. That's 7 books. I'm going to say that books C, D, E, and F all have to be clumped together as one big, I don't know, supergroup. How many objects do you have then? 4. Because you've got book A, book B, and book G, which are all singles. And then you've got the super Brangelina group of C, D, E, F. So you have 4 factorial because each of these groups can be rearranged in another order. However, the problem is that C, D, E, and F, those guys within the supergroup, they can like flip themselves around. Now, when we did the Brangelina one, we just times by 2. But this twist is a bit different here because C, D, E, and F themselves can get rearranged. And so rather than timesing by 2, we're going to times by 4 factorial. The reason why is within here, you have 4 choices for the first slot here, 3 choices for that slot, 2 choices for that slot, and 1 choice for that slot of these, like, of this subgrouping. Does that make sense? Because it's not just that Brad and Angelina can flip roles and just do it twice. It's that you can, like, rearrange any one of those combinations inside here. So if you almost wanted to write it out, you could write out 7 different slots. I'm just going to circle 4 of them in a row here. This is 4 times 3 times 2 times 1. But within this subgrouping, there's an extra 4, 3, 2, 1. So your answer is 4 factorial times 4 factorial. Or I guess you could write it as 4 factorial and then square it. That would also work.
Wait, what are the... Wait, there's nothing in the empty spaces?
Well, so I mean, this is book A, this is book B, and this is book G, for example. So you had like 4 choices for this spot, 3 choices for this spot, 2 choices for this spot, and 1 choice for that spot. But then wherever that supergrouping goes, within that supergrouping, you can rearrange all of those books as well. So it's almost like you have a puzzle inside another puzzle. Let me grab a manipulative here to help with this. Okay. Can you guys see how on the table I have 1, 2, 3, 4, 5, 6, 7, 8 different items there? Okay. And let's pretend that 4 of them, actually let's do the exact number we're supposed to do. Let's just remove this one here. And let's pretend that 4 of them all have to be like a subgrouping. So I'm just going to take 4 of them and I'm going to tape them together. So I'm going to put Emma's calculator together along with the ruler and the pen. And these guys are now all intertwined as a group. Does that make sense? So I know there's 4 things here because there's the front and back of her calculator, there's the ruler and the pen. But this is all one group. So now how many items are there? There's 4. Right? And you can rearrange these 4 items in any which way you like. And so that's why originally it's 4 factorial. But this group right here, depending on how I lay it, it could looks like say this, where it goes this part, then that one, then that one. I could flip it around this way and go this one, then that one, then that one, then that one. So really within the taped group, these guys right here, they all have to be in a row, but I can flip these guys around within their group as well. Does that make sense? So there's a 4 factorial within a different 4 factorial. 4 factorial. Exactly. Excited about math. Does that make sense? Alright, let's try the next one here. There's an organization. It's got 4 character ID codes. So as soon as I see 4 character ID codes, I know I've got 4 different things times by each other. Okay, it says the first character can be any letter other than O. So anything other than O, how many letters are there? So then 25. Okay. The last 3 characters are to be 3 different digits. How many digits are there? Okay, so there's 10 choices for this one. But then it has to be a different digit. Then this has to be a 9. And this has to be an 8. So we just need to multiply all those numbers together. Yeah.
How did you know?
0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay, that makes sense.
Okay.
Sorry, my brain's.
That's okay. If they don't give you more information, you're gonna have to,
Just guess.
well, not guess, but like just know that there's 9 numbers plus a 0 for 10.
Okay, got it.
What'd you guys get when you times all that together? 18,000 exactly. Okay. If there's 25,000 people and there's 18,000 passwords, did I have enough? Yeah. Does that make sense? Okay, why don't we move on? Let's start on the permutations notes then. You guys feeling okay with this so far? Alright, so let me show you a couple of examples of something that we've kind of done before, but there's like a new twist here. So, first one here, there's 15 kids at a birthday party. How many ways can children get door prizes if one of the door prizes is an animal, a gift certificate, and a DVD? So, how many prizes are there? 3 prizes. So I'm going to put 3 different lines because there's 3 prizes. And maybe I'll even write down, like, underneath here, this is the stuffed animal. This is the gift certificate. This is the DVD. It's supposed to be a C for certificate. So let's say I've got the gift certificate and I say, one of you gets the gift certificate. How many people could I give it to? Well, okay, that's true. I'm going to give it to one person, but how many choices do I have to give to? Yeah, 15. Yeah. Now, let's assume that at this birthday party here, once I give someone the gift certificate, I'm not also going to give them the stuffed bear or the DVD, because that's kind of a jerk move, isn't it? To be like, here, you can have all 3 prizes. So let's assume that after I give the kid the stuffed bear, he can't get the next prize. How many kids could get the gift certificate? And how many kids could get the DVD? Yeah. What about the remaining 12 kids? Nothing. Sorry, guys. Okay. I know it sounds kind of harsh, but there are lots of scenarios in life where not everybody wins. And I like to try to suggest this sort of scenario as a win-lose scenario. Okay? Where some people will get to win and have a prize, but a bunch of kids won't get to win and have a prize. And there's 12 kids who don't get the prize. Does that make sense? And yesterday I showed you guys that there's a special notation for this. It's 15 factorial over 12 factorial. Basically what that means is there's 15 kids total, but 12 of them do not get a prize. Like 12 of them don't win. Right? I mean, not everybody in life is a winner. This is such a common scenario that there's actually a special notation for it. We call it a permutation, but let me do one more example before I get to that. Let's say there's 15 kids on a grad committee. How many ways could you select a president, vice president, secretary, and treasurer? There are 4 different jobs. There's president, there's vice president, secretary, and treasurer. How many kids could be president?
1.
Okay, 1 can be president, but how many could? Good, okay. Well, okay, the kid who's president can't be vice president, right? So then 14 kids could be vice president, and then 13 kids could be secretary, and 12 kids could be treasurer. Does that make sense? This is such a common notation again that we've already talked about this. This is 15 factorial divided by what? What does the 11 mean? Yeah, the 11 kids who don't win, basically. Does that make sense? Okay. These are known as permutations. They're scenarios where not everybody wins, but it always drops by 1. I don't even remember why I have this slide anymore here. I think it was probably just to illustrate the idea of like there's so many different combinations you could have with like say your coffees, or you could have like just espresso or espresso and milk foam. And this is just the idea of like there's so many different possibilities that you could have that you got to memorize if you're a barista. I actually don't remember why I have this slide in here either. I think this was just to kind of remind you of a tree diagram. You guys remember tree diagrams from yesterday, just to count out all the possibilities? I think I found this online just to show you the idea that you can like flip around A and B. You could have this one be A and that one be B. This one could be A and that one could be B. This one could be A and that one be B. Or like flip all the way around. We talked about marble slab yesterday, didn't we? Or at least like Subway, the idea of like all the different combinations of stuff that you could, you know, like you could have chocolate and strawberry. You could have just chocolate. You could have strawberry and a waffle cone. Like when you start adding it up, the possibilities become fairly high. Anyways, here's the thing I want to show you that's new today. If you have a scenario that looks like this, where you have like say 15 times 14 times 13. I've already shown you that this is equal to 15 factorial over 12 factorial. If you have something that can look like this, where it's n factorial over n minus r factorial, we can kind of write what we just did using this notation. The 15 on the top would be 15. What is 12 equal to if it has to be 15 minus a number? What number do you subtract from 15 to get down to 12? 3, yeah. What this notation here is, it's the exact same thing. It's 15 over 12, but you can also write it as 15 over 15 minus 3. You know how I was just kind of saying a few minutes ago that the 12 is the kids who don't win? If 12 kids don't win a prize, how many kids do win a prize? 3. And that's what this notation kind of shows you, is that there's 15 kids total. And this 3 right down here are the number of winners. So as opposed to approaching it from like a losing perspective, this approaches it from how many kids actually do make the team, or how many kids actually do get a prize. And the way we write this then is 15p3. What 15p3 means is there's 15 kids, 3 of them get a prize. It's then implied that 12 of them do not get a prize. So 15p3 really implies this. Like I'll write this again. 15p3 really means 15 times 14 times 13. 15 kids total, 3 of them get to win. 12 of them don't. So you can actually type this in your calculator as like a shorter, faster way of writing out this notation. So here's how it works. First you type in 15, then go to math and go to that PRB, probability, just like we did yesterday. And you know how the exclamation mark is number 4? Just do the one right, second one down, NPR. And then after that, then pick 3. So the way it works is it's 15P3. I like to call it 15 pick 3. So there's 15 kids, pick 3 of them to win. And this is the exact same as 15 times 14 times 13. So that's like the shorter way of writing it, because it comes up so often that we need a shorthand notation for it.
Wait, you go to the PRB and then what?
So to go 15, then go NPR, and then pick 3. And that's the same thing as 15, 14, 13. If I were to go back to this question right here then, 15 kids and 3 of them wins, this could be written as 15p3. Like we just leave it at that. Like we wouldn't actually calculate the number. We'd just say 15 kids, 3 of them win. Whereas over here, it's 15 kids, 4 of them win. Does that make sense? Okay. I think I remember why I had marble slab back on there. At least the last time I went there, they had like Sundays where it was like you got to choose like 3 mixings. And like you got to choose any 3 of them that you wanted, right? So in a way you could count it up and say there are 17 different toppings there, and you get to pick 3 of them. Does that make sense? You don't get to have all 17 toppings, otherwise you'd probably be sick. But, you know what I mean? Like, there are lots of scenarios in life where you get to, there's a big list, and I'm going to choose that one, and that one. And then the rest of you, sorry. So, does that make sense? Go ahead, let's try some more examples. I keep forgetting why I put slides on here before. I think just to talk about the idea of how this overlaps with like passwords and security. You can kind of imagine that what we're trying to figure out here is different ways of making your, like the more combinations there are, the stronger your security happens to be. Does that make sense? Because there's more to run through, right? Like if there's only 5 combinations, someone's going to guess that combination, right? But if there's 17,000 combinations, that means that there's more password strength to it, right? Okay, let's try some more examples. This is the kind of unit where honestly, we just do a crap load of examples. Right? And that's the best way to kind of learn. So let's say you got some Scrabble tiles here, and you only get 3 of those letters. How many words can you spell? So I guess here's my first question. How many letters are there total? 1, 2, 3, 4, 5, 6, 7, 8. That makes sense? There are 8 Scrabble tiles in front of you. How many of them can you have? So 8P3, 8 pick 3. Which is the exact same thing as what we've been doing, where you just go, well, there's 8 choices, and then there's 7 choices, and then there's 6 choices. That just means the same thing now. That's all. One thing I should point out is this P scenario here has to be a scenario where you can only use something once. If you're able to use something again and again and again, then pick doesn't really work, because pick means that like there's 8, then there's 7, then there's 6, and there's 5, implying that once something's been used, it can't be used a second time. But there are scenarios in life where once something's been used, you could use it a second time possibly. So you need to make sure you're clear on that. So like for example, on this next one here, it says letters can't be reused. So it says first there's 2 different letters and then 4 different digits. How many letters are in the alphabet? 26. How many of them do you need? 2. So there's 26 letters. Take 2 of them. And then you need 4 digits. Well, there's 10 digits, from 1 to 10, I guess, or from 1 to 9 plus 0. But you get 4 of them. This is equivalent to saying 26 times 25 times 10 times 9 times 8 times 7. Whatever that number happens to be. Hello. You want breakfast? Cheese strings there. Thanks. What am I doing so far? Are you guys still with me? No. Okay, so there's 11 kids on the soccer team, and we want all 11 of them for a team photo. How do I write this then?
Thank you.
Great, 11P11. Yep. I mean, there is the possibility that there's 11 people and all 11 get to be on the team or be in the photo. Does that make sense? No? I mean, there are some scenarios where everybody's a winner. I don't know. Participation trophies.
Can we simplify it?
We could write this a few different ways. You could write this as 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This would also be equivalent to 11 factorial, by the way. All 3 of those things would get you the same number, right? Because in all 3 of those scenarios, everybody gets selected. There is nobody who gets left off the team. I mentioned last day, chances are for a lot of diploma questions, they won't actually calculate whatever that number is. Like you can go look up what 11 factorial is, and it's probably some astronomically large number. Often they won't even do that. They'll just leave it as like 11P11, and that'll be the way they phrase their answer. Or it could be something like A, B, P, C, D, and then your answers would be 1, 1, 1, and 1, I guess. Oh. It's pretty boring. Does that make sense? Let's do this one in a bit. I want to do some more examples first. Just remind me to come back to this one. Let's do some of these. These are all old diploma questions. I want to try some of these as a group. All right. So you have all these letters in the word kitchen, but the vowels must stay together. What twist is this? Okay. So it's the couple that you just can't keep them apart. So how many letters are there total? Okay. So treat one of them as they're a super group, like they're swished together. So there's actually only 6. And then what else do you have to times by? 2, I guess. Technically 2 is the same as 2 factorial, because 2 and 2 times 1 is the same thing, so D. Does that make sense? You get what I mean when I say you don't even have to do a calculation. You just have to be able to interpret which one of these things is the correct one. Okay, you got a multiple choice with 15 questions. 4 of them are going to be A, 3 is B, 6 is C, and 2 is D. How many different answer sheets can there be? All right. You can probably cross off A right now because we haven't talked about how C works. Just so you guys know, though, P stands for permutation, which was today's topic. If we get to the next topic, that's on combinations. That's what C stands for. It's not that one. Any ideas? Wait, how many questions are there? 15, right? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 questions. In a way, that's almost like 15 factorial. Here's the problem, though. Let's say you make the answer key, and the answer key looks something like this. A, B, then A, then D, then C, then D, then A, then B, and something like that. What if you flipped this A and this A around? Would you actually notice the difference? What do you have in this example, then? Identical objects, yeah. You have identical objects because this A and that A and that A, they all look the same as each other. It's like the 2 books that look the same as each other. So in order to solve the identical objects problem, you have to divide by how many of each you have. So since you have 4 A's and 3 B's and 6 C's and 2 D's, that's the answer. Because it's an identical objects question. The answer A looks the same as the other answer A. Does that make sense? Even though they might be in different locations, functionally they look the same as each other. Okay, you got a family, so you got mom, dad, baby, and 5 kids. How many arrangements are there if it has to end and begin with a parent? How many people are there total? I guess 8 technically with the baby. So 1, 2, 3, 4, 5, 6, 7, 8. What are my restrictions? Has to have parents on the end, right? So I guess in a way it could go mom here and then dad here. Or I guess you could go dad here and mom here. That makes sense? So here's one of the ways you could solve that. How many choices do you have for this first slot then, if you can be mom or dad? 2. Okay, well let's say you chose mom. Well, then the only choice left over here is that this one has to be dad. So it's almost like by default it forces the other one to be a 1. That makes sense? Because like if you have a choice of mom or dad here and a choice of mom or dad here, as soon as you choose that mom goes here, then doesn't it mean by default that dad has to go over here? Okay. And then now we have to intersperse the kids. So you've got 5 kids plus a baby, so 6 people total. Any restrictions on them? All right, so then 6 times 5 times 4 times 3 times 2 times 1. Okay, so this is an example where we actually do have to times all these numbers together then, because apparently that's the way they phrase the answer. Someone to help me out with that? I don't have my calculator nearby.
1,440.
That's one? Okay. If they didn't phrase the answer by actually timesing all these numbers together, here's another way they could have done it. they could have said that all of this information right here was 6 factorial, and they could have then asked you to times by 2, because basically there's a 2 right here, and times by 1 is kind of pointless. So they could have just said 6 factorial times 2. That also would have been the same answer. Still good? No. You've got a building, and out front there's 6 stalls, and we need 5 cars to go in the 6 stalls. How many different ways could those cars go in the 6 stalls? Any thoughts?
No car.
Well, like one of the stalls is not going to have a car. Does that make sense?
I would use 6.
Okay. So 6 factorial means that 6 times 5 times 4 times 3 times 2 times 1. 6 factorial. So is that kind of meaning that there's 6 possible cars that could go in this location, and then 5 possible cars that could go in this location, and 4 cars, and 3 cars, and 2 car, and then 1 car has to go there? I'm not really sure that fits there, because you can't actually have 6 cars go in this location. Does that make sense as to why I'm suggesting it? Although it's a great idea, I don't think that's going to work. I think, Brad, what you approached it from, I'm thinking here, is that there's 6 stalls, but it may be better to approach it as, think of the 5 cars. You got 5 cars. Okay. So Delver pulls up first. How many choices does he have of parking stalls? Okay. So D, Delver's sitting in the spot. Taylor then is the next one to show up. How many choices does she have for parking stall? And so Taylor chooses to go there. And then Haley pulls up next, and she's got 4 remaining choices to go for. And then Brad pulls up next, and so Brad takes that spot right there because he had 3 choices. And then Oakley pulls up, and how many choices does Oakley have? 2. Is there still 1 open stall? Yeah. Let's say that one more person had pulled up. How many choices of stalls would they have? Yeah, they would only have 1. So the correct answer for this would be 6 times 5 times 4 times 3 times 2. Another way of phrasing this, by the way, would be there's 6 different stalls, and we need to pick 5 of them to be used. That makes sense? I lied to you. You're actually right, though. There's a really weird twist here. 6 pick 5. Let's say that you actually did times by 1 at the very end here, even though that last person didn't show up. Does times by 1 actually change your answer? No. Although Brad was technically correct, I just wanted to make sure that it was for the right reason. This is 6 factorial, but it may be better to approach it as opposed to there being 6 like stalls. Approach it as like, well, there were 5 different cars, and this guy had 6 choices, 5 choices, 4 choices, 3 choices, 2 choices. The fact that there was 1 person left over times it by 1 was, I think, very convenient. Because although it is the same as 6 factorial, in a different scenario, you might get that wrong if you use that same logic. So I think 6 factorial is 120, or is it 720? 720, okay. 5 factorial is 120 then. Does that make sense? Okay.
Wait, so which one would be correct then? 5?
All of them. I mean, 6 pick 5 would have worked. 6, 5, 4, 3, 2 would have worked.
If it wasn't like that there was just 1, what one would be correct?
Let's say that it was 4 different cars parked in the stall. Let's change it to that. Okay. If there were 4 cars in the stall, I would say 6 pick 4. Does that make sense? Because there are 6 different stalls, and 4 of them need to be used. Does that make sense? But here's the thing: is that 6 pick 5 is the exact same thing as 6 factorial. But 6 pick 4 would not be the same as 6 factorial. It happens to work out that when you do 6, 5, 4, 3, 2, if you chose to times by 1, it wouldn't have changed the answer anyways. So. Is this the marbles one next? Okay. Okay, Okay, here's a particularly challenging one. Sometimes it helps to draw out the scenario. You've got one bag that has 4 different colored marbles. So here's a bag. And the marbles are going to be yellow, blue, green, and red, I guess. And then there's another bag, and it has 4 other marbles, but none of them are the same color. So orange, pink, magenta, and violet. Different colors now. Okay. So let's say a person reaches into the first bag and pulls out 2 marbles. So I reach in and I grab 2 marbles from this bag right here. What does that look like?
4P2.
Good, yeah. 4, and you want 2 of them. Does that make sense? What about in this other bag right here? Then this person reaches in and pulls out 2 marbles. It's also 4P2. Well, what do I do with this 4P2 and this 4P2? What should I do with them now? Okay, let's talk about add versus multiply. What does add mean? Add means an or. Did you reach into this bag or you reach into this bag? No, you reach into this bag and you reach into this bag. So if you have to do multiple things, and means multiply. So I need 4 pick 2 times by another 4 pick 2. So 144? Yeah, I was worried about that. Okay, there's a twist to this question I haven't covered yet. I should cover it now. Okay. How do I put this here? Even though, let's say you pick yellow and blue. Does it matter when you reach into the bag that you grab yellow first and then blue second? Or blue first and yellow second? I'd say no. In a way, when I reach in and I grab 2 marbles, the fact that they are different colors is great. But one of the problems is that we don't actually care which order we select them in. So in a way, this kind of becomes like the identical objects selection. Even though this is yellow and this is blue, you could say that this one was a winner, and that this one was a winner, and that these ones weren't selected. And so then what you have to do then is, you know how we have to like divide by similar looking objects? We have to divide by 2 factorial because these objects that we selected, although yes, they are different colors, functionally they're the same because they were both selected versus them being not selected. Does that make sense? And you have the same problem over here. I know there's an orange, a pink, and an M and a V, whatever I had there. But in a way, 2 of these are going to be selected, and 2 of them are not going to be selected. So I have 2 check marks and 2 X's. So I have to divide by the fact that the 2 that I select, functionally they look the same as each other. So I'm going to divide by 2 factorial. That changes us a little bit, doesn't it? What's 4P2 originally supposed to be? 4 times 3? That should be 12. So you guys would have originally had 12 by 12, I think, which is why you got 144. But what it actually should be is 12, but then when you divide by 2, it's actually supposed to be 6 by 6. So the answer is actually 36 on this one. Okay, that's the twist that we're going to talk about more in the combination set of notes and how to deal with that. But that is a huge twist there. Does that make sense, the idea, though, that when you select the marbles, that even though there are 4 different colors, that because we don't care really which one gets selected first, that although they're different colors, functionally you have 2 that get selected and 2 that don't get selected. And so the 2 that look selected look the same as each other, and the 2 that don't look selected also look the same as each other. So you have to divide by an extra 2 factorial. Well, you're going to buy some video games. By the way, I really like some of these names if you have a chance to read them. I think my favorite one is Legally Owned Auto. Grand Theft Auto. Legally Owned Auto. Dot Gobbler. Anyways. Okay, so you're going to go to the store, you're going to buy 3 action games. How many action games total are there possible? None. So 4, you need 3 of them. How many role-playing games do you need? Is that RPG role-playing game?
Yeah.
That's right. First. So you could have bought 3 of them, but you actually only take 1 home. And then there's 2 sports games, and you actually buy both of them. And then there are 3 classic games available, but you only take one of them. Tetris. Punky the Porcupine. Sonic, I think. Yeah. Does that make sense? Okay, we did one just like this before. Let's say that you have a practice diploma exam kind of thing, and 6 answers are A, 8 are B, 10 are C, and 9 are D. Do you guys remember how to solve a question like this? You have identical objects. The 8 B's, they all look the same. The 10 C's, they all look the same. So your first question is, how many total questions were there? 6 plus 8 is 14, plus 10 is 24, plus 9. There are 33 total questions. However, some of the A's will look the same as each other. Some of the B's will look the same as each other. Some of the C's will look the same as each other. And some of the D's will look the same as each other. That make sense? We just need to figure out whichever answer this one is then. What'd you get? A. Okay. Alright, why don't you guys try this one without me walking you through it first? See what you get. This is the most challenging part, is you gotta be able to take this word problem and interpret what the heck is happening. What scenario is this? Yeah, Brad and Angelina broke up. So they have to be in the same room, I guess, but we need a buffer. Okay, this is going to be a problem, having them right next to each other. So the method for solving this is find the total number of arrangements without any restrictions, that's 5 factorial. And then you subtract the ones where they are next to each other. And the way you do that is you treat them as though they're one grouping, so then there's only 4. But then you have to times by 2 just because you could flip-flop where they are. So whatever 5 factorial minus 4 factorial times 2 is. 72? Cool. Anybody get that without me showing you first? Good job.
You can write it as like 2 factorial, right?
Yeah, technically that 2 at the end could be 2 factorial, because really what you're doing is you're doing a 2 times a 1. Well, but I just like times it by 2, because you're just flip-flopping their order. Yeah.
Okay, so like the first number is like all choices?
Yeah, so if you have no restrictions, there's 5 factorial ways of arranging them.
Then the second number is like when there's two together?
Yes, so then what you're doing is you're saying, well, let's pretend that these are together. So then there's really only 1, 2, 3, 4 objects. So there's 4 times 3 times 2 times 1. But within this group, there's an extra 2 times 1. Because you could flip around the watermelon and the squash if you wanted to. So that's why it's a 4 factorial times a 2 factorial. Or you could just do times 2, because 2 factorial is 2.
I thought they said they don't want the pumpkins one mouse yet.
Right. So then that's why you take the total and you minus the ones where they are together. And if you take all of them and subtract the ones where they are together, the result must be the ones where they are not together. Yeah, for sure. Alright. Okay, so we just did one kind of like this. You've got how many letters in the word pencils? 7. But we have to keep the vowels together. How many vowels are there? I guess 2, right? E and I are the vowels. So treat E and I as one big group. So you actually only have 6 objects, and then you get a times by 2 factorial. Or times by 2, because you can flip those around. So 6 factorial is what, 720? So times it by 2, 1440? Okay, let me walk you through this next one here. We haven't done one quite like this before. Let's say that you have the following numbers to work with, 2, 3, 5, 6, 7, and you want to make even numbers. This is a twist we haven't come across yet. What makes something an even number? How does it make it even? That'll work. It's divisible by 2 is what makes it even. Okay. Let's go through some examples of even numbers then. Is 1 even? 2. 3, 4. Okay, so you got the pattern here. Maybe a better way of putting it is even numbers either end with 2, 4, 6, 8, or 0. Does that make sense? To make something an even numbers really depend on the last number. The last number must either be a 0, a 2, a 4, a 6, or an 8. If the last number is like 1, 3, 5, 7, 9, then it's odd. Does that make sense? Here's another twist. We want 3-digit numbers, or we want 4-digit numbers. You guys remember what OR means to do? Okay, so we need to add. So let's try it first. Let's try a 3-digit number. Here's a 3-digit number. How many choices do you have for the first number? Well, how many numbers are available here? I guess there's 5. Actually, I should be more specific here, though. The last number is so important, we should almost maybe start with that. How many numbers for that last number are either 0s, 2s, 4s, 6s, or 8s? Yeah, either the 2 or the 6. So I think before we even do anything, we should make sure that we use either the 2 or the 6 for that last digit then. How many numbers could go in the beginning then?
4.
Does it say that you can't reuse them? So I guess in theory, let's say that I use the 6 right here. Could I use the 6 right here again? I guess in theory I could. So I guess I should say I could use 5 numbers here then, because I could use any of the numbers. And it didn't say that I couldn't use repeats, so how many numbers could I use here? 5 again still, right? Because unlike in so many of the other examples, if you use a number and you can't use it again, you always drop the number by 1, right? But in this example here, it didn't say that you couldn't reuse numbers, so it looks like we need 5 times 5 times 2. So that's going to be, what, 50 combinations that you can use if there's a 3-digit password? Or, what if it's a 4-digit password? Okay, so let's start at the front this time. How many digits do you have to start with? 5. How many digits do you still have? They didn't say you couldn't reuse it, and you still have 5, but the last one's the only restriction. In order for it to be an even number, the last number has to be either my 2 or my 6. So then 2 possibilities.
You still get 300 if you add them together.
Because this is going to be 250?
Yeah.
And when you add them together, you get 300?
Yeah.
Okay, that should be the answer here. I don't like the way this one was worded. I think that they actually were implying, they should have said this here, no repeats. So the answer should be 300. But let's just redo the question, and let's use that assumption that I think some of you started with. Let's say you can't repeat a number then. How would that change it then?
That's not fine.
What was that?
Is that one from a...
I don't know. Sometimes they're not great at that. And sometimes they throw questions out, right? But this probably came off an old diploma, yeah.
Yeah, because what they really meant was just you're given those five digits.
But they weren't very specific, eh?
Yeah,
like they didn't specify no repeats, so yeah. Okay, let's try it again here then. I'm gonna throw 2 on the end of both of these ones here because that's guaranteed what I have to have. If I use up one of my even numbers right here, then would it make sense that you've only got 4 choices left for your first number and then 3 for the next one? And then for this one here, you've got 4 choices and 3 choices and then 2 choices. So like rather than having 5 and 5 and 5, 5, 5, because numbers aren't able to be used again, they're out of the rotation. Does this get you one of the 4 answers then?
Yeah.
Okay. 4 times 3 times 2, that's what, 24? That'll be 48. Add them together, you get 72. Yeah, for sure. So, my personal opinion, that first question really didn't have a right answer. I think it should be 300 based on the way they phrased it. But if you happen to not get one of the right answers, you may just want to try seeing whether repeats doesn't work and try one of their 4 answers, just to change it up. But I have a feeling this sort of question they should have thrown off the diploma afterwards, right? Like,
you would hope that one would just be tested.
Certainly. Yeah, you would think, right? I have diploma questions, though, that go back to, like, the late 1980s, though, so I'm not sure whether they were quite on that at that point. So, I don't know. Okay, why don't we try one more and then we'll take a break here. I think this is probably a good one to end on. Oh, right, I skipped a slide. You know what? Let's take a break, though, and then we'll come back to that slide I skipped. Does that work? Because it's already been an hour. So basically the possibility is that you've got your, your choices. You could choose mountain climbing. Or you could choose mountain climbing and canoeing. You could, in theory, select every single possibility. If this were me, for example, I don't like mountain climbing because I'm afraid of heights. I like canoeing. I like video games. I don't really like bowling, actually. I like billiards, and I like hockey. So I selected 4 of them. But did I have to select 4? I like pool.
Oh, never.
No, I mean, it's a certain variety of pool, but... So, I chose 4. But do you have to choose 4? Someone else might be like, I like canoeing and hockey, and that's it. I might select 2. So here's where this becomes a problem. You might want to do 7, pick 1, because you like 1 activity, but I might like 4 activities. Or you might like all 7. That really causes a problem, doesn't it? So there's a different twist to this. Treat this, remember how we talked about binary code yesterday, and how there's on-off switches? How many selections, how many possibilities do you have when working on the mountain climbing box? You could either put a check mark there, or you could not. So in the mountain climbing box, you have 2 possibilities. Either you like mountain climbing, or you don't. There you go, yeah, because then you have 2 choices here, 2 choices here, on or off, on or off, on or off, on or off. Your answer is 2 and 7. That's a curveball, hey? Because we've just spent so much of our time doing things like 7 times 6 times 5 times 4 times 3 times 2 times 1. But the answer to this one is, I'm going to guess, 50, 40? 128? All right. 1, 2, 2 to the 7 in my head. Does that make sense, though? That, after so long of doing 7 times 6 times 5, or doing, say, 7 pick 7 or stuff like that, sometimes they could throw a curveball at you and just be like, it's just 2 times by each other 7 times. How are you guys feeling on this stuff so far? Okay. Do you guys want to try combinations, or do you want to take the rest of the class just for some work time? What was that?
I think I need to
Okay. So just, why don't we do this? Go take a break. When you come back, I should show you that last slide I skipped, and then I'll give you guys the rest of the time to start working on an assignment. So just take 5 here. Do you guys have a bio test today?
Yeah.
Okay. Okay, so here's the slide I skipped. I throw this in as a contingency in case they give you a theory question. I've seen a handful of these total in my Lookings at Old Diplomas. But there is the possibility that they're going to ask you kind of like a, do you understand how the NPR formula works kind of question. So I just want to show you some of these in case. Okay, it's my contingency. So you could be asked, solve this for R. Like that's basically what this means is solve for R. Usually when they give a question like this, it's numeric response. R would be this little r right here. What sort of numbers would R have to be? Like what possibilities could it be? Could you use 5.7? -3? Basically R would have to be a whole number. Does that make sense? And so often I tell kids you could guess and check. You could do 3p1, 3p2, 3p3 and just see which one equals the same thing. But I do want to show you how to do it algebraically as well. So we're going to try to prove or solve NPR equals 3 factorial. What does the NPR formula? By the way, do you guys have your formula sheets up or nearby? Because the NPR formula is actually written on there somewhere. You guys find that?
It's n mark over bracket n minus r. That's the function. I think.
Yeah, that's the formula. You have that there on your formula sheet? Okay. So what I could do is I could write this then as 3 exclamation mark minus 3 minus r exclamation mark and make that equal to 3 exclamation mark. Does that make sense so far? Okay, well now to solve this algebraically, do you guys see how there's like a fraction here? What you could do is times the bottom of the fraction to the other side. So you can make it 3 exclamation mark equals 3 exclamation mark bracket 3 minus r exclamation mark. Well, I wouldn't FOIL it. I'm actually going to cancel. You see how I have a 3 exclamation mark on both sides? Well, 1 equals 3 minus r exclamation mark. Does that make sense so far? Well, we need this to equal 1. What exclamation mark equals 1? Like, for example, does 5 exclamation mark equal 1? Does 3 exclamation mark equal 1? 1 exclamation mark equals 1. So essentially, this 3 minus r needs to be 1. So I could add r to both sides, I guess, and make it like 3 equals 1 plus r. I could minus 1 from both sides, and I could say that r equals 2. Does that make sense? Now let's check it. Grab your graphing calculator. Try 3 pick, I guess 2 now, and then let's see whether 3 times 2 times 1 is also 6. Does that make sense? I'm gonna try another one here. Let's skip down and do C, just to save some time here. I don't think we need to do all of them. So on C, we're actually being asked to solve for n instead of r, but same concept. What does NP3 really mean? Well, NP3 means n factorial over n minus 3 factorial. That's what this little bit right here means. And that equals 4 of this stuff right here. What does n minus 1 p2 mean? Well, it means the first number is what goes on the top, so it's n minus 1 that gets factorialed. And then on the bottom, it's n minus 1 minus 2 factorial.
I
gotta pause there. I want to make sure everybody catches that because that's a pretty big step. So this n right here goes there and there. This 3 goes there. This n minus 1 goes there and there. And this 2 goes there. Okay, I'm just going to simplify one of them real quick here. This is still n factorial over n minus 3 factorial. There's still a 4 there. You have an n minus 1 factorial there. But what is n minus 1 minus 2? Yeah. See, I have an n minus 3 factorial over here and over there. We cancel. Right, next question. What does n factorial really mean, though? Well, it means start with n, times by one number less than n, times by two numbers less than n, times by three numbers less than n, and you kind of just do that for forever. What does n minus 1 factorial mean? Well, it means start with n minus 1, and then you got to pick a number 1 lower than that. So what's 1 lower than n minus 1? N minus 2. Then pick a number lower than that. Minus 3. And really, you keep doing that for forever. What cancels? Like almost everything, right? That cancels with this, and that cancels with this, and that cancels with this, and everything cancels with that, and we're left with NS4. That's probably enough for now. I just want to show you that there could be a question, a theory question involving your understanding of the NPR formula. So, to be honest, if you had to, you could probably guess and check though, because the numbers for N and R have to be whole numbers that are positive. You can't have negative objects or half objects. So you could almost just guess and check until you can confirm it's right. Okay, any questions? Okay, why don't we leave it there? Take a little bit of time and work on, I don't know, bio if you guys want to study for that. Tomorrow's Flex Friday, so I won't do a lesson on Flex Friday, but can you guys maybe start on the assignment a little bit? There's only one assignment for the whole unit. Yes, 17 questions. But the type of questions, though, are shorter, because like sometimes there's not a lot of work to them. Like all you have to do is time some numbers together.
Wait, what is it? Sorry.
What do you mean specifically?
Oh, our assignment, sorry.
Yeah, your assignment. So I know there's 17 questions, but like there's not part A, B, C for all of them. Like some of them have a part A, B, but. And then why don't we just do the combinatorics notes on Monday, and that'll kind of finish off those set of 3. Does that work? Okay. So I'll print off that assignment for you guys. That way you have a copy here.